capacitance again. It is very important to understand the capacitance inside the transistors. The first, we know that the two conductors separated by an insulator have capacitance. Its capacitance is determined by C equal epsilon area over distance, right? We have a capacitance. The similar structure we can find in the transistors. We have a gate to channel capacitance. That is very important, right? And also we have a source and drain capacitance to the body from the reverse biased diode, right? This is called diffusion capacitance because it is associated with the source drain diffusion. Let's take a look at this exact geometry. So we can approximate channel approximate the channel as connected to the source. So we have a source and drain. So this channel underneath connected. So CGS can be found by area. This is the area over distance, right? So COX times W times L. We define C per micron, assuming the L is the minimum, right? So typically most of the time digital circuits implemented in minimum channel length L min, but sometimes for custom design you may use larger, whatever you want, and greater than minimum channel length. But in this case we assume the minimum channel length is used. So typically C per micron is, in this example, 2 femtofarad per micrometer width of the transistor. Diffusion capacitance. So we understand how the diffusion capacitance come from the reverse diode, right? The reverse diode. But there's a layout technique that we can reduce the amount of diffusion area, so that we can reduce the capacitance. So capacitance depends on area and perimeter. So we can try to make the as small diffusion area as possible. So for example, if you want to stack 2 MOS transistors like this, you will have one MOS and the other MOS. Because this node is electrically connected, we can share the diffusion like this. And also there's no additional connection out of a middle node, so we can ignore that the contact, so we can even further reduce the diffusion area from here to there. So uncontacted diffusion area about half of the contacted diffusion area, right? So this varies, the minimum distance vary between process. Now, once we understood how the capacitance is formed, we can now move on to the switch function. So if you use just pass transistor alone, So MOS, we know the MOS can pass the 0 properly, and PMOS can pass VDD properly. So we are explaining again in this example. For VDD applied to the gate for MOS, the VDD trying to deliver upload to VDD, current need to flow in that direction. Then the maximum voltage it can go is only VDD minus VTH, because this node is gate and this node is source and drain from this current direction. So for this transistor to be on, GS must be greater than VTH. That's why the maximum voltage it can reach is VTH. Okay. So this is the derivation that we have, that I explained. You can read by yourself. So in this case, we say that we have the degraded 1 at the output. There's a simple some example for pass transistor circuit. For MOS, we know that this is the VTH is the maximum. For the PMOS, so current need to pull down like that, so maximum. So we know that current that way, so source and drain, so VSG must be greater than VTH P absolute. So the maximum voltage here can be VTH, the minimum voltage, I mean, it pull down from VDD. So minimum voltage VTH P absolute. To distinguish MOS and PMOS, I put the N and P there. For this case, we have, for example, in this node, again, the VDD maximum trying to charging up. So we know that this is the current direction for charging. So this is the max, the source and source and source, right? Drain, drain, drain. So maximum voltage here, it can pull down up till until it can I'm sorry, this is the pull up case. So we're trying to charging this up. So this is the source and drain, drain. So maximum this voltage should be greater than VTH. So this one, I'm sorry, this is VDD minus, right? VTH minus N. So this node is VDD minus VTH. Now, this node is VDD minus VTH. We know that this is again greater than this, the second transistor VGS greater than VTH. So this value can be VDD minus VTH. That one VDD minus VTH, right? So this guy VGS greater than VTH, right? All transistor, right? Satisfy this condition. For this case, so this voltage charging up, we are trying to charging up, so maximum it can go is VDD minus VTH. So gate voltage is now like that. So on the other side, the maximum is gate voltage plus VDD minus VTH minus VTH. That's the voltage can go up, right? That in that way VGS greater than equal to VTH. Satisfy. So VDD minus 2 VTH is the final voltage it can reach. This is the final answer. You can double check. Okay, we will move on to the next. Now to calculate the logic speed, we need to take into account resistance and capacitance so that we can find out the time constant. So it is very important to know the effective resistance out of a transistor. So the square law device model, namely Shockley model, is not very accurate for modern transistors. So it would be very complicated for hand analysis. So we want to simplify everything for digital circuit analysis. So we replace the IDS, the current and voltage relationship, with the effective resistance R, so that everything becomes passive circuit, the RC network. So it becomes very simple to calculate the delay and behavior. So actual switching happens. So for example, MOS and capacitor initially charged to VDD and it will go down. So let me draw that time versus voltage V out. Initially VDD, and if you assert the gate voltage to high, it will discharge, right? But at the moment we apply the VDD, device will be saturated, right? So device will be saturation region, meaning the transistor will work as the linear, constant current source with the linear slope there. This amount of current I is defined by the saturation region, half mu n COX W of L VDD minus VTH square. But once this output passes VDD minus VTH, that is overdrive voltage, let's say this is VDD minus VTH, this becomes the triode region. You get into triode, the saturation. So triode, saturation. So actual behavior is a little more complicated, but if you model that with the triode resistance, the difference between this actual model versus the simplified model doesn't have much difference. So we can pretty much model the resistance, pull down resistance out of a transistor with the triode region transistor resistance R. That is R on approximate mu n COX W O L VDD minus VTH. On. Now use the equivalent circuit for MOS transistors, which has the capacitance and resistance, both components, right? So you can construct with ideal switch plus capacitance and on resistance. So this transistor model can be approximated in gate capacitance and source capacitance and drain capacitance and on resistance, like that. The K is the unit device size. K equal 1 mean unit size, minimum size. So K, if you increase the device size, the resistance goes down, and if you increase device size, capacitance goes up, right? For the PMOS, the same relationship, right? But because of the mobility difference, for the same size, PMOS has a 2x larger R. So mu n over mu p, we know that that is equal to 2, assuming like this relationship, we can drive that resistance R as 2x larger than NMOS for the same size of device K, right? Here, K. In modern process, the capacitance for the same, for example, the gate capacitance and source and drain capacitance are about the same, which is 2 femtofarad per micron of gate width. For example, 10 micron gate width that leads to around 20 femtofarad gate capacitance and source capacitance and drain capacitance, right? CGS, CSB, CDB to body, right? So these values very similar across many processes. This is kind of rule of thumb. The resistance is 0.6 micron process, 6 kilo ohm times micrometer. So this improves with the shorter channel length. So minimum contacted device, one minimum contact device size of the unit transistor, that is 4 over 2 lambda. So it may be in this process 1 micron wide width, so L looks like 0.6 micrometer. If the 0.6 micrometer, then this is 2 lambda, so 4 lambda is around 1.2 micrometer. So it is around 1 micron, right? That is a minimum, probably. So we just assume that unit transistor size is 2x larger than minimum channel length, width of the minimum channel, width of the minimum device, unit device, is we assume that like this relationship. Let's think of the fan out of one back-to-back inverter, two inverter stages. So input capacitance, each gate capacitance of the unit device will have the C-in. This is the C-in, C, and the source and drain also will have a C-in, C for the parasitic. So we have a 3C. For the load, we have the 3C. So C load versus C in is fan out. Fan out is now 3C over 3C equal to 1. So in this configuration, we'll try to estimate the delay. So we can find an equivalent RC network. So we have one resistance, NMOS for the R unit transistor will have R resistance R, and since mu n over mu p equal to 2, for the 2x larger size of the PMOS, we get the same resistance as the NMOS resistance. So we have a parasitic capacitance, source and drain, and also parasitic capacitance of the PMOS source and drain, like that. And we have the gate capacitance here, right? CG, G gate capacitance. This is source drain, Yes, CD. This is CD. This is the CS, right? So we can find the equivalent network. Once we found the equivalent network, we will find additional network for pull down. So NMOS will pull down. So this resistance path. So total 2cc, 2cc will be shown on the Y node. So this node will be eventually go down VDD to ground, right? So in this operation, the original, it will go down with the RC time constant as time goes by, like this. So this one, so it will go down exponential 1 minus t shifted by t0 over tau of VDD. So V out will be like this. So the delay from this T0 to when it passes the half VDD is approximately same as tau. So if you calculate the exact mathematics, the T0, so the time, if you find the time of the V out approach to half VDD, then you will get the T equal 0.69 tau when and V out equal to half VDD. So this is kind of the delay for the step input applied. The delay estimation is 0.69 from this moment to half VDD. So knowing this fact, the time constant through this network is tau is R total 6C. That's the time constant. But typically input, it doesn't comes with this step input. It has a finite RC time constant from the previous stage. So roughly we can estimate the delay from here to there is approximately TD, and TD approximated by the tau. This is something that approximation make your life easier. So from this calculation, the D is the delay from A to I, from A to Y, that is defined by time constant tau.